If we only look at a tissue slice through the lens of RNA expression, or only through protein markers, we end up with blind spots. Biological systems operate across multiple molecular layers, so analyzing them one at a time limits our understanding of the tissue's true architecture. The problem with combining these datasets is the scale mismatch. A spatial transcriptomics read captures thousands of RNA transcripts per cell, while a spatial proteomic read might only capture a few dozen surface proteins. The feature counts and statistical distributions are completely different. SpatialGlue is designed to solve this scaling problem. It starts with 3 distinct inputs: the physical XY coordinates of a cell, or spot, on the tissue slice, and the raw expression matrices for modality 1, like RNA, and modality 2, like protein. To build an accurate, unified map of the tissue, the algorithm first has to corral these incompatible, mismatched data types into a shared mathematical space. SpatialGlue processes each modality twice. First, a spatial graph maps a spot to immediate physical neighbors. Next, a feature graph maps that spot to others with similar biological profiles. Both enter a GCN encoder, producing 2 representations, HS and HF. For a single data type, like RNA, the system now holds 2 competing mathematical profiles for the exact same cell. Now the algorithm has to decide which representation is more reliable for identifying this cell, its physical location or its biological similarity to others. SpatialGlue uses a within-modality attention layer to adaptively weight the 2 graphs, merging them into an optimized block for modality 1, Y1. With optimized blocks for both RNA, Y1, and protein, Y2, complete, what does the second half of this dual attention mechanism do? The between-modality attention layer balances the modalities themselves, producing a single dense cross-modality representation, Z. Z then passes through a decoder to reconstruct the original matrices. If reconstruction fails, a loss loop triggers a signal to adjust the attention weights and try again. This continuous cycle of encoding, weighting, and decoding forces the model to refine its math until the final representation, Z, accurately reflects both the biological feature similarity and the physical reality of the tissue. Once trained, the model outputs a highly detailed, clustered spatial map generated directly from that integrated Z representation. We can see the results in mouse spleen tissue data. SpatialGlue successfully identified specific macrophage subsets, like the MMM-Phi cells, located across 3 distinct zones that unimodal tools entirely missed. This chart shows the modality weights assigned during the spleen analysis. Looking at the violin plot for the MMM-Phi cluster, the algorithm heavily weighted the protein data over the RNA data, compensating for regions where the RNA signal was too noisy alone. Here is the complete SpatialGlue data flow. We start with the inputs, build the 2 graphs for each modality, encode them through the GCN, apply within-modality attention, apply between-modality attention, and generate the output map. By giving the system the ability to adaptively assign value to different data types, SpatialGlue maps tissue architecture accurately by calculating exactly when to listen to RNA and when to listen to protein.